add stuff. So this effect, the melting point depression, is part of a larger trend of things that you see when you bring species into solution. And they're called colligative properties. And they essentially all rely on the same idea that, you know, if I take A, let's say A is essentially the host, right? The solvent. It could be a solid or a liquid, but it's what you're going to dissolve B in. So you have a lot of A and you put some B in. That by definition, the chemical potential of both species goes down. Because for the solute, you can write that mu B is mu B naught plus RT log the activity of B. And as you know, in some cases, right, we write that as the mole fraction, but not always. And since the activity is less than 1, the chemical potential of B in the solution is lower than that in its pure state. And again, if it weren't, it would just fall out. And the reason that the chemical potential of A goes down is simply a dilution effect. Mu A is mu A naught plus RT log the activity of A. And again, if we assume Raoultian behavior, then this becomes the mole fraction of A. So then this is mu A naught plus RT log the activity of 1 minus XB in the solution. So chemical potential of A goes down because it's being diluted, and chemical potential of B goes down because it goes in solution. So let's now think back of the melting point depression. So what's really going on here is that I set up the condition that things can dissolve in the liquid state, but not in the solid state. So by allowing the liquid state to make a solution, I am favoring it, right? Its free energy goes down and the chemical potentials of the species go down. So in the liquid state, G is lowered by the entropy of mixing. And so what does the solid have to do? Well, the solid can't lower its free energy by mixing, right? Because it can't mix. So the only way that the solid can lower its free energy relatively to the liquid is by going down in temperature. So the only place where you can find, you know, the solid having a lower free energy than the liquid, so you lower the temperature. So it's the only place where there can be an equilibrium. And if you look carefully at the equilibrium condition that we found, it kind of shows the physics. We found that RT XB in the liquid is minus delta H of melting of A divided by T times the shift in temperature. And look carefully at that equation. This here, what is that? That is essentially this term at small xb, right? It is the term RT log 1 minus xb at small xb up to a minus sign. So this is the entropy stabilization of the liquid. This is the amount of free energy by which the liquid is lowered through the solution process. And what we're saying is that has to be equal to this here. And what is that? Look at that carefully. Look, what is this here? Approximately. It's the enthalpy of melting of A divided by the temperature. This is approximately its entropy of melting, right? It would only be its entropy of melting if T is exactly the melting temperature. But since T remains close, so what am I writing here? I'm writing the shift in free energy of the pure A liquid and solid with temperature, right? Because this is their entropy difference of pure A liquid and solid, and I'm multiplying that by delta T. So you can see the balance here, right? So this is the entropy stabilization of the liquid. This is how I stabilize the solid by going to lower temperature. So this is stabilization of the solid by going to lower temperature. By dropping T. So the new melting point is where these new forces are in equilibrium, right? Does that make sense now? Does it also make sense to you now that the properties of B do not matter? Because the effect of B only comes up entropically. It comes from the dilution of the chemical potential of A. Right? So the effect in this model, the effect that B has on A is simply that it dilutes it. And therefore that it lowers the chemical potential of A. So there is no thermodynamic property of B present here at all. There's no energetics present. It's just entropy. And entropy is just counting, as you know from statistical mechanics. And this is why melting point lowering is so prevalent. Because it's sort of independent of the physics and the chemistry. And this is really an important concept you should keep in mind, because what it means is that if you plot a phase diagram, the beginnings of it, and you start, say, at pure A, and here you have a melting point, that almost always the melting point starts out going down. Whatever's on the other end. And again, this is why you can melt ice with salt, right? You know, this is 0 Celsius for ice. Salt is way up there on my roof at 900 Celsius. But lo and behold, the melting point of water starts going down when you add salt. So what is the one assumption that can break this? We made a critical assumption, right? The critical assumption here is that there is no solution competition from the solid. When we did this derivation, if you go back to the last lecture, we said A and B can only mix in the liquid state, but not in the solid state. So this is how we disfavored the solid, right? So if the solid state also has good solubility for B, then this is not as simple anymore, right? Because now the solid can also lower its free energy by absorbing B through, and thereby lower its free energy through the entropy of mixing. And of course, the limit of that is when both of them are ideal solutions, which is the first derivation we did. So if both of them are ideal solutions, then they can both mix really well. And then you find that the melting point of the mixtures is just essentially an interpolation between the melting points of the two pure end members. Okay? But this case is much more common just because of the physical nature that it's harder to dissolve stuff in solids than in liquids, because in solids you don't have as much space and things can't move away. Okay. So I want to go through a few other colligative properties, because all of them show a way that you can balance the entropy effect on solutions with some other force. And the other one that's kind of very common is osmose, or osmotic pressures. And the idea is that if I have a state of pure A and I bring it in contact with, I'll sort of make a pipe here that can go very high. And in the pipe is A plus B, so some solution. And they are connected through a semi-permeable membrane. And this membrane only lets A through. So it's selective for A. So it does not let B through. Then the question is, can you ever reach equilibrium here in this situation? Because, so since the only species that can move is A, you have to look at the chemical potentials of A. And what is the chemical potential of A in the pure state? Well, here, right, mu A, let me call this alpha and this beta just to distinguish. Mu A and alpha is mu A pure plus nothing, right, because it's pure. And what's mu A here? Well, again, here mu A, this A is diluted by B. So here is going to be mu A in the reference state plus RT log the activity. If I assume it's Raoultian, I'm already going to write XA, so I'm going to write right away that it's log 1 minus XB. Okay, so here I have made the Raoultian approximation, right? So obviously these cannot be the same, right? Because if the reference states are the same, this term here is always negative, so the chemical potential of A on the right-hand side is always lower. So what is the only thing that can happen? Well, so A would stream through the membrane into the pipe. And if the pipe just sort of overflows somewhere, then there is nothing you can do. You will literally suck the A dry, because you can never get a concentration of pure A on the right-hand side. Now, if this pipe keeps on going, then what's the compensating mechanism, which ultimately brings us in equilibrium? It will be pressure, right? So if this fluid here can rise, then at some point it will apply pressure at the membrane, okay? And that added pressure will raise the chemical potential there. So what's the change of chemical potential with pressure? What is the mu A dP? Let you think about that. I'll take some coffee. What is the mu A dP? This you're going to have to know, right? And faster than this. You can still tell me before I finish it. Are we getting closer? I can switch the derivatives. Getting there? What is the GDP? That's the volume, right? So I'm taking the derivative now of NA with respect to the volume. So this differential, as we have shown before in the class, is the partial molar volume of A in solution. So how the chemical potential in a solution responds to pressure is the partial molar volume of that species. Okay, so let's do this. So if a pressure gets applied to the right-hand side, then mu A, which is equal mu A naught, has to equal mu A beta, which is equal mu A naught plus RT log 1 minus XB, and I apply pressure, so plus the partial molar volume of A times some delta P. These go away. And so I'm again going to approximate this as minus XB. And so what you find is that the pressure that builds up, if you solve that, is RT divided by the partial molar volume of A times XB. It probably wasn't smart of me to rewrite it this way, because this way it just looks like a formula. If I put the pressure on one side, right, if I write delta P times the partial molar volume of A is equal to RT XB, then what do you see? You see again, entropy stabilization of A, right, is being compensated by the mechanical contribution to the chemical potential of A now. So it's essentially the sum of these two that has to be zero. Well, it's a sum of this minus that one that has to be zero, right? So this is entropy at work. This is the chemical potential lowering of dilution. And this here is mechanics to compensate. And what do we already know about mechanics versus chemistry? You know, maybe we already know the song, It's a Small World. It's a small world after all. Okay. If you're in mechanics, it's a small world. The chemical forces are small, which means that if we're trying to fix something chemical, the pressures we're going to need are very large. So let me calculate that for you, and then we'll try to do something useful with it. So I was going to calculate the osmotic pressure of seawater in contact with pure water. And unfortunately, seawater is not the same everywhere in the world. So I took seawater with about 0.6 moles of salt. And if you convert that in mole fraction, which I'm sure you know how to do, then the mole fraction of salt is 0.6, and then you need to know the number of moles, you know, per liter and blah, blah, blah. And so you get to 55.55. So the actual mole fraction is 0.0108. Now that's moles of salt, like say sodium chloride. So the number of ionic species I'm going to have is actually twice that, right? Because like salt is mostly sodium chloride, but that's going to dissociate to sodium plus chlorine minus. So I'm really going to have ×2 this in terms of dissolved species. Okay, so what is the pressure if I apply that equation there? For once, I'll actually put in all the numbers. 8.314 joules per mole per Kelvin times 298 Kelvin divided by 18 times 10 to the minus 6 meters cubed per mole. So I took the partial molar volume of water to be equal to just the molar volume, since the water isn't very diluted, times 0.0108 times 2, because I have dissociation. So if you put that all in SI units, you find that this is 29.7 times 10 to the 5th pascals. Or it's basically about 30 ATMs, right? 30 atmospheres approximately. So, like I said, right, if you do mechanics, it's a small world because you need 30 ATMs, right? You need 30 ATMs to simply overcome the chemical potential difference of water in pure water versus seawater. So in principle, this column here will rise to how high? How much is 1 ATM in height of water? I mean, it's roughly 10 meters, right? So 30 feet. So approximately, if any of you are divers, you probably know that, right? So 1 atmosphere overpressure is approximately 10 meters of water. So this is basically 300 meters of water. So this tiny effect, which seems kind of meaningless, that you just happen to have some salt in the water, can create a mechanical osmotic pressure that sends the water 300 meters high. So in terms of mechanics, colligative effects are extremely important, right? So they can create a pressure of 30 atmosphere and 300 meters of water. So you can kind of invert this problem and do what's called reverse osmosis to purify water. Let's say I have seawater and I want to make pure H2O. So I could put a membrane here, right? So this is a membrane that transports H2O. So if I apply pressure on it from this side, and here P is just 1. If I apply greater than 30 ADM, then I push out. But if I apply greater than 30 atmosphere, then I push out the water and I push it into the pure state. So this is a way that you can make pure water out of seawater by applying pressure. Is this practical? Yeah, this is actually done. Reverse osmosis with pressure is actually done. And while this seems like a high pressure, remember that the energy cost is what matters, right? It's not, you know, energy is only force times displacement. So if I don't displace a lot here, I still don't have a lot of energy. I just have to be able to make a construction with a membrane that can withstand these pressures. And unfortunately, a lot of these membranes are polymers. And so, you know, it's sort of hard to build membranes that can withstand these high pressures. And then, of course, if you want to do this and you want to make millions of gallons of water, you can't make a little cylinder. This has to be an enormous amount of piping. And the problem is that on the sea side, water side, you get all kind of crap in, right? And you get fouling and algae growth and all that stuff, which love to grow on polymers. The other example that I show in the slides, but it's only one slide, so I don't want to call it up, is in biology. If you have cell membranes, if this is a cell, you know that they've told you, like in lab, never to drink like purified water or distilled water, right? I mean, as a good rule, you should not drink anything in the lab that comes in containers in the lab. But even if you were 100% sure that it's distilled water, you should not drink it because it literally can kill you. And while we're all told to drink a lot of water, there is like with everything, there's a point of excess. Because what happens, so cell membranes in your body are essentially osmotic membranes. And in the cell, you have a lot of salt, right? You know, in the cell, what is a cell? It's basically a bunch of water and then a bunch of ions, right? So the chemical potential of the water inside a cell membrane is reduced, it's lowered. So if you surround this by pure water, what happens? You know, the pure water wants to go in the cell because that's where its chemical potential is lower. But if too much water goes in the cell and the salt cannot get out fast enough, what happens? Your cell bursts. So if you drink like gallons and gallons and gallons of distilled water, you will die. And you will die simply by exploding your cells. But there is, like, of every devious thing, there is a good use of this. And what do you do when you have old lettuce sitting in the refrigerator and you want to serve it to your guests and make it look better? Or you never do that, or you would never do that, of course. You crisp it, right? It's called crisping. So you put the lettuce in water, and you kind of like, then put in one of these swingy things where you dry it. And that's not just washing it. What actually happens is that the membranes in the lettuce take up water, and they sort of bulge out like bodybuilders, right? And the lettuce looks much crisper again. And that's a process of osmosis. So the water in which you washed it gets soaked into the lettuce and makes it crisper. It just doesn't last very long, so you have to tell your guests to eat fast, or the lettuce is going to look bad again. So, desalination of water is a big deal, right? We all claim we're short of water all the time. If I asked you, like, what the minimum energy cost is, what the minimum amount of energy is to create pure water out of seawater, how would you do that? The reason I'm asking you is some of you should engage in conversation with me, and some of you should actually think about how to solve this. You can kind of divide yourself up. The reason is that I have seen many people, even in high positions, get this totally wrong because they don't know thermodynamics. So I hope you're going to do better. So thermodynamics, I'll tell you, can make a statement about what the minimum energy cost is to get water out of salt, or salt out of water, whatever you want it to be. So what do you think that is? Let's say you were asked this, and I'm not kidding you. There is a theoretical limit, a minimum amount of energy you need, and I have seen the Department of Energy write proposals with targets that were like a factor of 10 below that theoretical limit. This is how bad it is. So how would you get that theoretical limit? I hope you've thought about it. If anybody wants to make a suggestion, that's good. Otherwise, do you know the statement, otherwise I'll derive it for you, that if you're trying to do a process at constant temperature and pressure, then the minimal work you need to do is the delta G of the process. In differential form here. Are you familiar with that statement? I didn't actually explicitly derive it for you, I realize. But some of you have seen this undergrad. You need a derivation, or? Okay. No participation. Okay, then I'm going to actually for now assume that you know this. So the amount of reversible work, I'm going to write W prime here, I'll explain in a second, is the dG of the process. The reason I write the prime is that this is the not PV work, because I don't really care about that. So it's whatever extra energy I have to put in. Okay, so let's apply this to a water-salt mixture. I'm going to treat water-salt as an ideal solution for sake of argument. So I have H2O here. I have salt here, called Sol. And you know, somewhere here is the concentration of salt in seawater, right? Let's say that's our salt concentration with which we work. So I could calculate what the delta G of mixing is. Right? I mean, I could put it in like RT log this and RT log that, right? So that would give you a number. If you ran a competition, would you win? Would you get the lowest number? Is this the lowest amount of energy? Is this the lowest amount of energy you can like, by which you can create? I'm going to formulate my words carefully here, so you probably should listen to them. Is this the lowest amount of energy by which you can create pure water out of salt water? This is important, right? Half of the world is trying to do this, right? If you live in Saudi Arabia, anywhere in Arabia, Singapore, any waterlocked country, unless you like to steal it from Malaysia, but sorry for my Singapore friends. Everybody's trying to do this, right? So is this the best process, is what I'm asking you. It's not, right? I mean, because why? What you're doing here is you're taking the mixed state and you're separating into water and salt. But you're engineers, right? Who cares about the salt? I don't want the salt. What's the best I can do is seawater. And I want to get the H2O out, or some H2O out. What's the energy change in that process per mole? So here I have H2O plus salt. Come on, folks. This is when your engineering neurons should get super excited. What is the energy of doing this? Pulling water out of salt water. I take a mole of H2O. Let's say this is very large. I take a mole of H2O out there. By how much am I changing the free energy here? What's the quantity that tells me? What is the quantity that tells me when I add a mole to something and the thing's very big?
Potential.
Yes, the chemical potential. So when I take the water out of here, the energy is minus mu H2O in seawater, right? And then when I make it pure, I get plus mu H2O pure, right? So what's the energy difference between these states? So the minimum work difference between pure water and water in seawater. And this is why you take MsC2O1a. This is a much better solution. And why? Because I don't care what happens to the salt. I'm taking large volumes of seawater and I'm just plucking water out of it. But I'm not upgrading the salt, basically. The salt stays in the seawater. Whereas if I do unmixing, then I'm upgrading the water and the salt. So this costs me much more energy. See that? This is why distillation costs you much more energy overall, also because it involves enormous energy inputs that you have to recover. You can calculate, if you want to make pure water by distillation, you should calculate once how much energy it takes to both heat and then boil a mole of water. And it's a big number. And then you have to recover all that to condense it, because otherwise you have way too much energy input, right? Okay, let's calculate what this number is. Very exciting. So the difference in chemical potentials, so the work, this is going to be, this is basically, this is going to be, this here is mu naught plus RT log, XH2O, and XH2O is going to be written as 1 minus X salt, right? We're making all the same approximations as before. So the work is going to be RT log 1 minus the mole fraction of salt in seawater. Okay, put in numbers. At room temperature, 8.314 joules per mole per Kelvin times 298 times the log of 1 minus 2 times 0.0108, numbers I've used before, and you find that it is 54 joules per mole. Or if you like it per liter, is the way you would sell it, it's 3 kilojoules per liter. Or if you're going to do this with electricity, then you may want to know how much this is in kilowatt hour. 3.6 kilojoules is a kilowatt hour. So this is approximately 0.83 kilowatt hour per liter. Is that a lot? I don't know. Would you pay like, let's say roughly 1 kilowatt hour, right? Would you pay a kilowatt hour per liter of water? Depends, right? What's a kilowatt hour? I mean, if you do it with electricity, wholesale, somewhere a kilowatt hour would roughly be about wholesale. If you're industrial, sort of 10 to 15 cents at most, right? Dollar cents per kilowatt hour. So it's not very expensive, right? So when I did that, I came to, it's about 12 cents. The theoretical price is about, with this rate, is about 12 cents per cubic meter of H2O. Wait, I think I'm off by some unit here. Yeah, okay. Sorry. Yeah, this is, of course, this is not 0.83 kilowatt. This is per 1,000 liters. A cubic meter, right? So it's about 12 cents per cubic meter, which is the sort of common sales volume of industrial water. Okay, that's the theoretical minimum. You cannot do better. In reality, the best plants do about a factor of 2 of that. So because plants have overhead, right, and they need excess driving force, and they need to turn on the lights, and so plants run at about twice that. But as you see, there's not a ton of room for improvement, right? Like it's not like you're going to make desalination like a factor of 10 cheaper than it is today. Okay. I mean, there are other things you can do, right? Like you can try to get access to water, like brackish water, which is what they do in a lot of countries. So that doesn't have as much salt as seawater, right? Because then your chemical potential differences are less. But the number you really should remember, right? 3 kilojoules per liter. That's your essential number for your basis for extracting water from seawater. Okay, so that's it on colligative properties. So Jenny, if you could stop.